In 2017, a planetary scientist published a paper that most of his own colleagues thought was wrong. Not slightly off, fundamentally, structurally wrong. The kind of idea that gets quietly ignored at conferences rather than debated. His name is Shi Zhang, a professor at UC Santa Cruz, and the claim he made was this: that the thin, hazy atmosphere clinging to a small, icy world 4 billion miles from the sun was behaving in a way that shouldn't be possible according to everything we understood about how planetary atmospheres work. He said Pluto's atmosphere wasn't being controlled by gas the way every other atmosphere in our solar system is. He said it was being controlled by haze itself, by tiny solid particles acting as the primary engine of the entire atmosphere's temperature, heating and cooling it directly. A mechanism that, if true, would make Pluto's atmosphere unlike anything else we had ever studied anywhere in the solar system. Most of his peers were skeptical. There was no way to prove it. The telescope capable of actually testing his prediction hadn't even launched yet. The telescope finally turned its instruments toward Pluto for the first time in this specific way in 2022 and 2023, and when the data finally came back, confirmed and published in the spring of 2025, it didn't just support Zhang's idea, it proved he had been right about something that, by every existing model of atmospheric physics, genuinely shouldn't have been happening at all. This is the story of what the James Webb Space Telescope actually found when it looked at Pluto for the first time in mid-infrared light. Why the results confirmed an idea scientists had spent 8 years doubting, and what it might teach us about the very origins of life on Earth. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this discovery matters, you have to go back to where the story of modern Pluto science really begins, on July 14th, 2015, the day NASA's New Horizons spacecraft became the first, and to this day, only spacecraft to fly directly past Pluto. After a 9-year journey covering more than 3 billion miles, New Horizons gave humanity its first real look at a world that had been nothing but a fuzzy, indistinct blur in even the most powerful telescopes on Earth for the previous 85 years since its discovery in 1930. What it found stunned planetary scientists. Instead of a dead, featureless ice ball, New Horizons revealed a world with genuine, active geology, vast nitrogen glaciers slowly flowing across. A heart-shaped basin now known as Sputnik Planitia, mountain ranges made of water ice rising several miles high, and an atmosphere, thin but real, layered with a delicate blue haze visible in backlit images taken as the spacecraft looked back at Pluto from behind, with the sun shining through the atmosphere from the far side. That haze became the center of a genuine scientific puzzle almost immediately. Pluto's atmosphere is composed primarily of nitrogen, with smaller amounts of methane and carbon monoxide, and through a process of photochemistry, sunlight breaking apart and rearranging these molecules high in the atmosphere, it produces a complex haze of hydrocarbon particles, similar in basic chemistry to the thick orange smog that shrouds Saturn's moon Titan. In the immediate aftermath of the New Horizons flyby, atmospheric scientists tried to build models explaining how Pluto's atmosphere maintained its temperature, and those models ran into a real problem. The standard assumption in planetary science is that a thin atmosphere's temperature is governed primarily by its gas content, the same basic physics that governs Earth's atmosphere, Mars's atmosphere, and every other atmosphere we had directly studied up to that point. But when researchers tried applying that same gas-dominated framework to Pluto, the math didn't add up cleanly. Something else appeared to be involved in regulating the atmosphere's energy balance, something the standard models weren't accounting for. This is where Shi Zhang's 2017 paper enters the story. Zhang proposed something that ran directly against the conventional wisdom of the field, that the haze particles themselves, not the surrounding gas, were the dominant mechanism controlling Pluto's atmospheric temperature. In his model, these microscopic haze particles absorb sunlight and then re-radiate that energy away as heat, primarily in mid-infrared wavelengths, meaning the haze wasn't just a visual feature drifting passively through Pluto's sky. It was actively driving the entire thermal engine of the atmosphere, heating and cooling it directly. A roll haze doesn't play in any other atmosphere scientists had studied anywhere else in our solar system. Not on Earth, not on Mars, not on Venus, not even fully on Titan, which has its own haze but a very different, much thicker atmospheric structure overall. Zhang has openly described how his own colleagues reacted to the idea at the time, calling it, in his own words, a crazy idea. But buried inside that crazy idea was something crucial for good science, a specific, testable prediction. If haze really was cooling Pluto's atmosphere the way Zhang proposed, then that haze should be emitting detectable mid-infrared radiation, a very particular thermal signature that, if found, would essentially prove the mechanism was real. The problem was that no telescope in existence at the time was sensitive enough to actually detect it. Pluto is small, cold, and extraordinarily distant, and the specific infrared signature Zhang's model predicted required an instrument more powerful than anything humanity had yet built. That instrument arrived on Christmas Day, 2021, when NASA launched the James Webb Space Telescope, and among the 4 scientific instruments on board is one called MIRI, the mid-infrared instrument, purpose-built to detect exactly the kind of faint thermal radiation Zhang's prediction depended on. In May of 2023, an international research team led by scientists from the Laboratory for Instrumentation and Research in Astrophysics at the Paris Observatory and the University of Reims, Champagne-Ardenne, pointed Webb's MIRI instrument at the Pluto-Charon system and captured something that had never existed before in the history of astronomy, a high-quality mid-infrared spectrum of Pluto and its atmosphere, spanning wavelengths from 4.9 to 27 microns, a spectral range that had remained completely unexplored on Pluto simply because no previous instrument, not Hubble, not any ground-based observatory, not even New Horizons' own instruments during its historic flyby, had the sensitivity to capture it clearly. Alongside that spectrum, the team also obtained separate thermal light curves, essentially continuous brightness measurements taken as Pluto rotates at 4 specific mid-infrared wavelengths, 15, 18, 21, and 25 microns, allowing scientists for the first time to track how the thermal emission from Pluto and its large moon Charon changes as each body spins. The results, published across a series of papers in astronomy and astrophysics in April 2025, and then in a headline study in Nature Astronomy on June 2, 2025, confirmed Zhang's 8-year-old prediction almost exactly. The mid-infrared thermal emission Webb detected matched what his model said should be there if haze particles really were the dominant driver of Pluto's atmospheric energy balance. Zhang himself, reacting to the confirmation, noted how rare this kind of validation actually is in his field. In planetary science, he explained, it is not common to have a hypothesis confirm this cleanly within just a few years of proposing it, and he described feeling genuinely lucky that the timing worked out this way. What Webb's data proved is that Pluto's atmosphere really does operate on a fundamentally different mechanism than the atmospheres of Mars, Venus, Earth, or virtually anything else we've studied up close. It is a haze-dominated atmosphere, not a gas-dominated one, meaning the tiny hydrocarbon particles drifting through Pluto's thin nitrogen sky are not just a passive byproduct of the atmosphere's chemistry. They are actively running the entire thermal system. A genuine first in planetary atmospheric science, and by the standards of the models scientists had built before this data existed. A mechanism that, strictly speaking, shouldn't have been the dominant process at play at all. But the mid-infrared observations revealed something else, something even the researchers didn't initially expect to find with this level of clarity. Involving Pluto's largest moon, Charon. Charon orbits so close to Pluto and is so large relative to it, nearly half its diameter, that the two bodies are technically considered a binary system by many astronomers, rather than a simple planet-moon pair. Unlike Pluto, Charon has no atmosphere at all, and its surface is dominated by water ice mixed with ammonia-based compounds, a very different composition from Pluto's nitrogen and methane ices. But Charon's poles show something strange, distinctly darker reddish coloring that has puzzled scientists since New Horizons first photographed it clearly in 2015. The leading explanation, strengthened significantly by this new Webb data, is genuinely unusual. Methane molecules escape from Pluto's thin atmosphere, drift across the roughly 12,000 miles of space separating the two worlds, and eventually land on Charon's poles, where the extreme cold and constant exposure to space radiation chemically transforms them into complex reddish hydrocarbon compounds called tholins, the same general class of organic molecules found on Saturn's moon Titan and thought to be a key ingredient in prebiotic chemistry. In other words, one world's atmosphere is quite literally raining down material onto its neighboring moon, chemically altering that moon's surface in a way that doesn't happen anywhere else between any two bodies in our entire solar system. Webb's new thermal light curve data allowed researchers for the first time to place real quantitative constraints on the thermal inertia, emissivity, and surface temperature variations across different regions of both Pluto and Charon, giving scientists their clearest picture yet of exactly how this strange one-way atmospheric exchange between two worlds is actually unfolding. There was a second, independent prediction embedded in this research too, one made in 2023 by Linfeng Wan, one of Zhang's former doctoral students, and a co-author on the new Nature Astronomy paper. Wan's earlier study had modeled exactly what Charon's own thermal light curve, the pattern of its brightness, variation as it rotates in mid-infrared light, should look like if the methane transfer hypothesis was correct. When Webb's actual 23 observations came back, the measured light curve amplitude for Charon agreed closely with Wan's theoretical prediction. A second confirmed forecast from the same research group, adding further weight to the idea that this cross-world atmospheric transfer really is happening the way scientists have proposed. Zhang has been careful in discussing these results publicly, to place Pluto's atmosphere in a broader context rather than treating it as an isolated curiosity. He's pointed out that Neptune's large moon Triton and Saturn's moon Titan both have similar nitrogen and hydrocarbon-based atmospheres, full of their own haze particles, and that this new understanding of how haze can dominate an atmosphere's thermal behavior on Pluto means scientists likely need to reconsider the role haze plays in those other atmospheres too, potentially reshaping how we understand atmospheric physics on icy worlds throughout the outer solar system, not just on Pluto itself. And then there's the connection Zhang has drawn that reaches all the way back to Earth's own deep history, one that gives this entire discovery a weight well beyond simple planetary curiosity. Long before oxygen built up in Earth's atmosphere, roughly 2.5 billion years ago, life already existed on this planet. But the atmosphere surrounding that early life looked nothing like the air we breathe today. It was overwhelmingly nitrogen-based, rich in hydrocarbon chemistry, with essentially no free oxygen at all. An atmospheric composition that, in its basic chemical ingredients, actually resembles what we now understand to be happening on Pluto right now. By studying exactly how haze particles behave, form, and interact with nitrogen and hydrocarbon chemistry in Pluto's extreme distant environment, Zhang and his colleagues believe researchers may gain genuinely new insight into the atmospheric conditions that existed on Earth. During the specific window of time when life was first getting established here, billions of years before photosynthesis ever introduced oxygen into our air at all. In that sense, a 4 billion mile distant, minus 380 degree world at the very edge of our solar system may be quietly holding clues about the conditions that allowed life to take hold on our own planet in the first place. It's worth being precise here about what exactly was new in 2025, because Pluto has, of course, been observed before, first by New Horizons up close in 2015 and by various ground-based and space telescopes for decades before that. What was genuinely unprecedented about this specific observation campaign was the wavelength range and the instrument. Webb's MIRI observations captured Pluto's mid-infrared thermal signature in a spectral window that had simply never been accessible before. Not because nobody had thought to look, but because no earlier instrument, including New Horizons' own onboard cameras and spectrometers during its historic flyby, had the sensitivity required to detect it clearly from this kind of distance. This was, in a very real and specific sense, the first time humanity had ever seen Pluto in this particular kind of light, and it revealed a physical process, a haze-driven atmospheric engine that had been theorized but never actually confirmed, hiding in a wavelength range we simply hadn't been able to access until this telescope existed. This same broader Webb research campaign extended beyond just Pluto and Charon too. Using its near-infrared spectrograph, a separate instrument from MIRI, Webb also studied more than 75 trans-Neptunian objects, the broader family of icy bodies, including Pluto, that orbit the Sun beyond Neptune on paths shaped by the ancient migration of the ice giants Uranus and Neptune during the early formation of our solar system. Scientists had expected these distant ancient bodies to be dominated by simple frozen molecules, water, methane, carbon dioxide, altered over billions of years by solar radiation into more complex hydrocarbon compounds like methanol and ethane. Webb's new data confirmed that basic expectation, but in NASA's own words, in unexpected ways and in unprecedented detail, allowing researchers to sort roughly 60 of these objects into distinct spectral classes based on the specific chemical fingerprints Webb detected in their surfaces, giving scientists their first real large-scale chemical map of this ancient, distant population of worlds. So here is where this actually leaves us, honestly, in the middle of 2026. A prediction that most planetary scientists doubted in 2017 has now been directly confirmed by the most powerful telescope ever built, revealing that Pluto's atmosphere runs on a genuinely unique mechanism, unlike anything else discovered anywhere else in our solar system. One where solid haze particles, not surrounding gas, control the entire thermal balance of the atmosphere. A strange, one-way transfer of material from Pluto's atmosphere to its largest moon has now been measured with real thermal precision for the first time, explaining the reddish stain at Charon's poles as the visible result of methane molecules crossing empty space and getting chemically transformed by cold and radiation once they land, and a distant world, 4 billion miles from where you're sitting right now, demoted from full planetary status back in 2006, has become an unlikely case study for understanding the very atmospheric conditions that may have existed on Earth during the earliest chapters of life itself. None of this required inventing anything. The actual verified science here is stranger and more genuinely surprising than most of what gets exaggerated about this distant little world, because it took a scientist willing to propose an idea his own colleagues initially dismissed as crazy, and a telescope powerful enough to finally prove he was right. If this kind of story is what you come here for, one that respects the real science instead of manufacturing a fake one, hit subscribe and turn on notifications, because there's a lot more of the outer solar system left to explore. Drop a comment telling me whether you think Pluto deserves its planet status back, and share this with someone who still thinks Pluto is just a boring ball of ice at the edge of nowhere.